Okay, so it looks like we've got everybody ready to go. All right. So Newton's first law, right? Things keep doing what they're already doing, especially they stand still. If they're already standing still, they tend to stand still, and things that are moving in straight lines, constant speeds can continue doing that unless acted on by a net external force. Newton's second law, what does that force do to an object? It accelerates it. And how it accelerates it is that a certain force will accelerate a certain masses, a certain amount based on their mass. If it's a smaller mass, it'll accelerate it more. If it's a bigger mass, it'll accelerate it less. And the equation force equals mass times acceleration expresses that in a mathematical way. So force equals mass times acceleration. Force equals mass times acceleration is a vector equation. So it's not just linear, it's not just one-dimensional, it can be two-dimensional, three-dimensional, which means just like with kinematics, you can split the force equals mass times acceleration equation into dimensions. And you can say, what is force equals mass times acceleration in the x dimension? What does it look like in the y dimension? What does it look like in the z dimension? After you've split up all your vectors, all of your kinematic vectors, all of your force vectors into components and arrange them into different dimensions. So what looks like one equation can actually become two or three equations based on how many dimensions you're dealing with. The movement, how the movement goes essentially. And that is force equals mass times acceleration in Newton's second law. Here's an example of Newton's second law, the rocket cart or the rocket sled. This was used by NASA to test the ability of humans, astronauts, and also their equipment when they were accelerated at very high accelerations. So you have these 4 rockets on the back of the sled. Each one of these rockets provides some thrust, which is a force. There's also some friction fighting against the movement of the sled. The sled has a weight to it and has a normal force associated with that weight as the sled is pressed down into the tracks. And there's an acceleration from these thrust vectors, right? And they tell us the acceleration of the sled and the mass of the sled and the friction that the sled feels, but they don't tell us what the thrust is. And here's the free body diagram for this. You draw a point to represent the sled, 4 thrust vectors, you just stack them one on top of the other so you can see that that thrust is rather big. The friction vector pointing backwards, normal force up, weight down. Very simple diagram you can see right away kind of what's going to happen here. And then you do the math. In the y direction, the math is easy. Why is the math easy? In each direction, this equation is true. In each of the cardinal directions, this equation, force as a vector, is equal to mass times acceleration as a vector. In the y direction, what this means is that all the forces, if you add them all together, the sum of all the forces in the y direction equals the mass of the sled times the acceleration in the y direction. But we happen to know that this sled is on tracks and it's not accelerating in the y direction. Y is up and down. It's not going to go flying up off the tracks upward, and it's not going to go flying down through the tracks to the ground. So we know that this is equal to 0. And that means we know that the sum of all the forces equals 0. That means we know that the normal force, which is up, plus the weight force, which is down, so I put a negative on it, is equal to 0. And that means that the normal force and the weight force are equal, but opposite, right? As far as the x direction, we know that the sum of the forces is equal to mass times acceleration, and the acceleration is not 0. It's definitely accelerating because they've told us it's accelerating. So that equation gives us something different. Force net equals mass times acceleration horizontally. The net force is the 4 thrusts. You add 4 of them together, you get 4 times the thrust, minus the friction, because it's in the opposite direction, in the negative direction. And then that has to equal the mass times acceleration. And the thing that we don't know is the thrust. So we take this equation here, we take this equation here, and we solve it for the thrust. And you get 4 times thrust equals mass times acceleration plus friction in that case. Then we go ahead and we solve this. They're leaving the 4 on the left side, and that's fine. You can put it on the right if you want by dividing. But whatever you want to do, mass times acceleration, we know the mass, we know the acceleration, we know the friction. We put all those on the right side, plug them all in. We get a number, 1 times 10 to the 5th newtons, and then divide it by 4 to get the individual thrust of one engine. It ends up being 2.5 times 10 to the 4 newtons, which is a pretty reasonable amount. I mean, it looks like a big number. This is 25,000 newtons essentially per engine, but that's actually not that big of a number. For example, if you've ever seen rock climbers rock climb, up the rock, they have these little aluminum rings called carabiners, and a carabiner has a maximum strength of about 25,000 newtons. So at 25,000 newtons, the carabiner will break. And so that's not a huge amount of thrust, not a huge amount of force, but it's a fair amount of force. Actually, I think it's 2,500 newtons for a carabiner. I could be wrong. The cord that they use, that's actually called ribbon. The webbing that they use between those things is more like 25,000 newtons. But anyway, that gives you an idea. Some jet engines have far more than this, have like in the millions of newtons of thrust. But jet engines were generally much more powerful than the small rocket engines they put on these little sleds. And the sleds were quite light, so they still got a lot of acceleration out of them. On these sleds, they were actually able to get accelerations that were like 10 times, 20 times, 30, 40, 50 times as much acceleration as we feel from gravity. So a lot of acceleration. Turns out that humans can only handle about 100 times gravity without like their whole body coming apart, inside out. So these are the 3 equations that come out of Newton's second law in the x direction, the y direction, the z direction. And they can all be solved separately, but they can also be used to help solve each other once you've worked them out a bit, because they do have similar things in them. They all have the mass in them, for example. The accelerations and the forces can have parts in them that are the same as well. So we'll see that here as we move on. So here we have a 400 gram ball, which is 0.400 kilograms, talking about, right? Kicked across the field by a player, and it goes through this acceleration. This acceleration is now a vector. So now we're in 2 dimensions. It has 2 components, an I hat component, J hat component, X and Y. And we want to find the resultant force acting on the ball and the magnitude direction of that force. Well, Newton's second law can be applied to the vector itself. You can actually write the net force equals the mass times acceleration and write it just like this. So we've put the entire vector in the equation. The vector equation works just fine. And when you multiply the mass times the acceleration, you will get the force. So that is the force that the ball feels right there. But it's in vector form. So maybe it doesn't tell us as much as we'd like to know. It doesn't tell us the magnitude of the force, for example. But we can actually find the magnitude of the force by using the Pythagorean theorem. So we use the Pythagorean theorem with the force vector up here. Square the 1.2, square the 2.8, add them together, take the square root, and you get a magnitude of 3.05 newtons, right? 3.05 newtons is not that much force. Remember, newtons are, let's see if I can remember how many newtons. I'm going to say it's about 5 newtons make up 1 pound. Is about, I think that's about right. So it's about 5 newtons per pound. So this is only about, 3/4 of a pound-ish, 2/3 of a pound or something like that. Yeah, we're not kicking this very far, right? We're not going anyplace. This is like when you see the little kids playing soccer and the field is like the size of, like half the size of their bedroom. And they have the tiny little pop-up nets on each side. That's the kind of kicks you're getting out of those kids right there, right? Except for that one kid that's like twice as big as everybody else, running over everybody. That's the game that everybody wins. Anyway, here we have an angle that we can calculate from the x and y components, right? Take that y component divided by the x component, take the inverse tangent, we get 66 degrees. 66.8 degrees. Yeah, and this is the reason that nobody likes to weigh themselves in newtons. So you get up to somebody and say, well, how much do you weigh? Well, I weigh 1,000. Nobody wants to be weighed in newtons. I don't want to weigh 1,000 newtons. That sucks. I'd much rather weigh pounds. I'm not going to say what that is in pounds. You can figure it out yourself. But, you know, we like pounds because it's a lower number. If we weighed ourselves in stones, it'd be even a smaller number. But that's what they used to do in England. They used to use stones, which was actually a measure of mass. But you say, oh, I'm like 3.5 stones. They also have slugs. Yeah, slugs is another measurement.
Slug is like 7 pounds.
Which is great because, you know, then I'd only weigh like 30 slugs. I'm like 30 slugs. I lost a slug this morning. But if you gain a slug, you know, if you gain a couple of slugs, that could be a lot of weight. So anyway, nobody likes to weigh themselves in newtons. Here's the mass of a car. We're going to find the mass of the car rather. If a net force of negative 600 newtons in the j hat direction produces an acceleration of negative 0.2 j hat meters per second squared. Now, this is a legitimate question because we can see here that we have a negative j hat direction for our force and a negative j hat direction for our acceleration. That should always be the same. Those should always be in the same direction. The net force and the acceleration always in the same direction. That's something that Newton discovered. Okay, so we're going to find the mass of this car. Now it's a pretty small force. I mean, 600 newtons it's a bigger number, but this is still less than, this is probably the average weight of people. The average weight of a human in the United States is probably around, you know, 600 newtons or somewhere between 600 and 800 newtons or somewhere in that range. So if that's probably higher than that. This is like 120 pounds or something, 110 pounds. Average, I don't even know what the average weight of a person in the United States is, 180, 190, 200. I know that I'm more than that. That's all I know. But anyway, but I'm almost 50. I have an excuse. I have gray hair and grandkids. I'm allowed to have
Grandkids?
Yes, I have 2 grandkids. Can you believe that?
Not really.
Well, thank you. I take that as a compliment.
Your kids are like still in college.
I do have kids in college still. I have 2 kids in high school still. My oldest is done with college and she's married and living in Chicago.
3 kids?
I have 6 kids. So, all right. Anyway, enough about me. Let's talk about Newton. All right. So we have a net force. We have an acceleration, both point in the same direction. That's good. So now we're going to apply this. We're going to put these things into our equation. Our equation is mass equals force over acceleration because we've solved it for the mass. And we can actually use a one-dimensional version of this. We can get rid of the vector quantity because we're only using one dimension. We're only in the j hat dimension. So we don't necessarily need to think of it in terms of multiple dimensions at this point. So we just plug our numbers in. Remember, so they decide to not use the signs for this, the 600 newtons and the 2 meters per second squared, or the 0.2 meters per second squared, but you might as well because it still has direction. Even when we're into one dimension, it doesn't take away the vector quality of it. So there's still direction. You could put the negatives in. It would give us the same answer because we have negative 600 newtons and negative 0.2 meters per second squared is still going to give us 3,000 kilograms for the mass. And 3,000 kilograms for the mass of a car is totally reasonable. That's pretty normal. That's actually pretty average for a car. What's that? Yeah, maybe a Honda Accord. A Civic is probably a little lighter than that. I would put a Civic at around 1,500, 1,600. But this is an average car, kind of your average sedan kind of car, smallish, one of these small SUVs. Like I have a Honda CRV, which is essentially just a Honda Accord with big tires on it. Or maybe it's a Civic with big tires, I don't know. But anyway, that's pretty average. That makes sense. That's reasonable. For just as a quick conversion, 1,000 kilograms, which is called a metric ton, is not very different than a English ton. It's about, the kilogram is measuring mass, of course, but if you measure the weight of 1,000 kilograms, the weight of 1,000 kilograms is 10,000 newtons. And 10,000 newtons is about the same roughly as 2,000 pounds, which is the same, which is the English ton. So a metric ton and an English ton are about the same weight on Earth. So that would be 3 tons essentially. So here's an example, another 2-dimensional example. We have a particle that has 1, 2, 3, 4 forces on it. The particle drawing is the same as is essentially the same as the free body diagram. It's not much different. I don't know if they drew a free body. They didn't draw one because it's about the same. They tell us the mass of it. It's a pretty massive particle, 4 kilograms, more like a bowling ball. But anyway, they tell us the values of the 4 forces, and they want to know the acceleration of the particle. So these are in 2 dimensions. We're going to have to treat it 2-dimensionally. We're going to have to add these forces together in the x direction and the y direction separately. So they do that. They split it into an x direction and a y direction. They split all the forces into their components. And then they put the components in when they're adding the forces in the x direction. This one here is the component from F1 cosine 30. And then they subtract off F3 because F3 is pointing in the negative direction, and it's completely in the x direction. So it's all of F3. It's not any component of it. It's just the complete force. And then they, when those are summed up, they equal the mass times the acceleration in the x direction. So that acceleration that they're going to get from this is only the component of the acceleration vector that's pointing in the x direction. It turns out to be 0.92 meters per second squared. So it's going to end up moving in the positive direction at this speed. In the y direction, they do similarly, except there are 3 forces to deal with in the y direction. They have 1 component of force 1, F1 sine 30, and then F4 and F2 are only pointing in the y directions, F4 in the positive y direction, F2 in the negative y direction. So you have a positive and a negative there. That's equal to m times the acceleration in the y direction. And then you plug in your numbers and you can calculate for the acceleration in the y direction. Now we have the components of the x, the x and y components of the acceleration vector. We can build our vector from there, and that's what it looks like. You can also calculate the magnitude and the direction using the Pythagorean theorem and the inverse tangent if you would like. Now, they do something in this chapter that I really despise because we haven't learned about momentum yet, but they're going to introduce it to us anyway. It turns out what momentum is it's something about movement. It's a mathematical calculation from movement information that is always preserved in a situation. So if you have a system that's undergoing movement with forces, and you account for all of the movement and forces in the system, and then you calculate the momentum at the beginning, before anything happens, calculate the momentum at the end after everything happens, the total momentum in that isolated system. By isolated system, I mean there's no external forces coming in and there's no external forces going out. Okay. There's no forces going out to external parts of the system. So the system is not affecting its surroundings. The surroundings are not affecting the system. So if you have a system like that, then this momentum thing that we calculate by doing some math, which we'll learn about later chapter, is always the same before and after. And that's really interesting because we're often looking for things that are conserved. One of the most commonly known things that was thought to be conserved was mass. It was a famous experiment done where they filled a bulb full of oxygen. They burnt a candle inside the bulb and they put the bulb on a scale with some masses that were balancing it out. And as the candle burned and it disappeared and went away and there was no more candle, the scale never moved. In other words, all the mass that was in the candle was still inside the bulb. It was just in a different form. And you could actually see it in the bulb because the bulb filled with smoke and the inside of the bulb got all dark with the soot and everything else. So it turned it into gas and particulate matter that kind of was floating around the bulb, but it was still had the same amount of mass. The mass didn't actually disappear. And so it was thought by chemists and scientists at the time that mass is preserved. In other words, mass cannot be destroyed, cannot be just created out of nothing. It's always there, it just changes forms. And that was thought to be the truth for a couple hundred years at least. But that one turned out to not be actually true. And scientists are always looking for something like this, something that always stays the same, something that always is there in nature. So that one was kind of shot down by Uncle Albert in 1917 or something like this, when he wrote his papers on the general theory of relativity. No, was it that paper? I can't remember which paper it was actually. It might have been a different paper. But anyway, one of the papers that he wrote in the early 20th century, he proved theoretically that you could actually create energy from mass and you could create mass from energy. And so that mass wasn't always going to stick around, but it was only in extreme circumstances. And he couldn't even test it. The circumstances were so extreme that nobody was able to test his theory until decades later. And during World War II, when they were trying to make atomic bomb, they were able to demonstrate that the extreme circumstances where you create a nuclear reaction inside the nucleus of an atom, the nucleus of the atom actually loses mass when it releases the energy from the nuclear reaction. So, and that's what his famous E equals mc squared equation is. Energy equals mass times speed of light squared. And that's what that equation is describing. It describes the fact that energy on the one side of the equation is equal to mass on the other side of the equation. And then the equality factor in the equation is the speed of light squared. And why that is well beyond the scope of this class. But if you continued on into physics, you would spend an entire semester learning about why that's true. And then you would be enlightened with 20th century knowledge. The short version is that things are weird when you're looking at atoms. Atoms are weird. They just are. Anyway, so why is that interesting here? Well, momentum, it turns out, a specific kind of momentum, not the momentum we're talking about here actually, but there's another type of momentum that is related to this that is absolutely conserved as far as we can tell. We have never, in every situation, even crazy things going on with atoms and smaller particles than atoms that are even weirder than atoms, even with those particles, momentum is conserved always. So this is a momentous discovery that momentum was conserved. Now, another really interesting thing about momentum being conserved is that the discovery of momentum being conserved happened quite a while ago, back in the, I want to say late 1700s, early 1800s, sometime, a couple hundred years ago. They discovered this, but they weren't sure what they were seeing. In fact, they were discovering two things at once. They were discovering the momentum was conserved in one hand, but they were also learning about energy and energy being conserved, because that's another thing that people thought was conserved for a very long time until Einstein came along and said, well, you can turn energy into mass or mass into energy. Can't turn momentum into energy. Momentum doesn't disappear from the universe. It's just moved around. And, you can give something part of your momentum, or you can take some momentum from something else, but it just kind of gets passed around the universe. But the interesting thing about this being discovered a couple hundred years ago is that one of the people that defined the difference between energy and momentum, because they're very similar in many ways, especially mathematically, but one of the people that did it was a woman. And you think, well, no big deal, but you guys were all born in the 21st century. If you go back even 100 years to the beginning of the 20th century, it was rare to find a woman in science, even at the beginning of the 20th century, which is the century I was born in. In fact, even when I was born, it was rare to find women in science. In the 1970s, it was rare. Okay. But if you go back 200 years or more, not only was it rare, but society forbade it. It was illegal in some places for women to even go to school. And so for a woman to be involved in this was really quite amazing. And the situation was interesting because it was in France. And in France, you had this society at that time, it was before the French Revolution. You had this society that was based on the ultra mega rich and the ultra mega poor, essentially, right? And you had some people in between, but not many. And the ultra mega rich had all the resources and all this time on their hands, and they mostly spent their time sleeping until like 2 or 3 in the afternoon, getting up, getting ready for a party that night, and staying up and partying until 5 or 6 in the morning, and then going home and eating dinner and going to bed and sleeping till 2 or 3 in the. That was like their entire life, and that's why the poor people hated them, because the poor people worked their butts off to support this lifestyle. But there were a few people that were much different than that. A few of the rich people used their money and their time and their resources and their education to study science. And one of these families was the family of Du Châtelet. And they had a daughter, Emilie Du Châtelet. They also had sons, a few of them, I don't remember how many. But all of their sons were scientists, and the father was a scientist, and they all worked together doing science. And they discovered that the daughter was actually the smartest of them all. And the things that as she would listen to them talking and watch them doing these things around the house, she was interested in it, and they actually allowed her to participate, which was a huge thing. Because back then, even within the same family, men and women wouldn't like do the same things. They wouldn't even hardly like hang out together sometimes. It was like two separate worlds. The divide between the sexes in Europe was astonishing to the people that live now. But in this family, it wasn't. In this family, they actually encouraged her and educated her at home personally in the sciences. And she ended up being so much smarter than the rest of her family that pretty much everything they did was her work. But they couldn't give her credit for it because people would lash out against them if they did. So they created a pseudonym for her. They created a fake person, a fake name for her, and they published her work under this fake name. And eventually they were able to actually give her that credit. It took them some time to do it, but they were able to do it, which was amazing. It didn't hurt that as she grew up, she was not only smart, but she was quite beautiful. And if you were quite beautiful at that time, of course, it was easier to marry you off. Of course, rich people could get married off because of their money anyway, but marrying your daughters off was kind of like a sport in Europe. And so it's like trading like sports cards or something. It was a stupid system at the time. But anyway, that kind of was still the case in her family. She ended up marrying somebody that was dumber than she was and didn't really respect him. But she ended up actually hanging out with and purportedly having an affair with a very famous, very brilliant man of the time, maybe the most famous and most brilliant man of the time, in Voltaire. Voltaire was very close with Emilie du Châtelet. And so it didn't hurt that she had powerful, forward-thinking men in her life, her brothers and her father to begin with, and then Voltaire, who was, just a rebel against society and did everything that nobody ever wanted anybody to do, because he was enlightened. He knew that the human race was meant for better things than trading daughters on the marriage market in Paris or whatever. So she actually participated in this work, and she was the one that defined the difference between energy and momentum and created this discussion about momentum being conserved, energy being conserved. So it's not talked about much, unfortunately, even today, where we consider ourselves so forward thinking. We still don't talk about many of the great scientists of the past who were actually women that made huge contributions. But we're doing better. We're bringing light to the women that worked in NASA during the space race in the 50s and the 60s and the 70s, with the movie Hidden Figures and the book The Rocket Girls. And if you haven't read those books, Hidden Figures or Rocket Girls, I highly recommend it. Rocket Girls? I think it's called Rocket Girls. I don't know. I have it at home. But those books were the two ones that I think Rocket Girls came first and Hidden Figures came second. But both of them are great books that are give a great insight into not just women in science, but the science in general, because it was affected greatly by the interaction between men and women working together and they overcame the sexual barriers in our society far before politicians did, way before politicians did. Like the scientists were fighting for women to be in science because they recognized the brain of the woman rather than just the woman. You know, they looked at them and saw, oh, this is a smart person. They didn't look at them and say, oh, this is a woman. They just looked at them as a person. And it's the same with race. Race was overcome by scientists long before it was overcome by society and by politicians, because scientists look around and they're looking for brains. They're not looking at skin or anything else. They're just like, I want somebody who's smart. This person's smart. Bring them in. And so it's an amazing thing to see that we're finally kind of seeing this come to light. And I mean, my dad worked for NASA in the 70s during the Apollo program. He worked at NASA and they weren't allowed to really talk about those things. So I never knew it and I grew up around it. You know, if they talked about it outside of work and it got out that they talked about it, they'd lose their job. They'd lose everything. They'd never be able to work in science again because of the politics. The politicians made that illegal, not the scientists. So anyway, it's an interesting connection here that goes back hundreds of years, this idea that we have this momentum thing that was discovered hundreds of years ago by a woman in a society that didn't allow women to know anything or do anything. But this relationship between force and momentum, it turns out to be one of the more important things that Newton was able to put together, that force causes a change in this thing we call momentum, this movement quantity. So they actually talk about, what they're going to do with this is they're going to actually take the derivative of momentum, because that's the relationship. They're going to take the derivative of momentum in time and calculate Newton's second law, which is what he actually did to come up with Newton's second law. So they do the derivative of momentum, happens to be mass times the velocity vector. You do a derivative of that in time, you get mass times acceleration, and you have Newton's second law. Man, we're not getting through this. We're gonna have to push this off till next week because I talk too much.
You see the person on back then?
Yeah, we'll definitely do that. I'll do that really quick before I forget. So we'll put chapter 5 homework, finish up with chapter 5 homework next week. Whoops, that's not what I want. But let's go ahead and see what else we can drive through here. So section 5.4 is all about weight, right? Weight is just the force that we feel when gravity pulls us towards the surface of the earth and we run into the surface of the earth. So gravity is always pulling us towards the center of the earth, but we don't always feel gravity. We don't always feel it. For example, if you jump out of an airplane, you don't really feel it. You feel the effects of it. You feel yourself accelerating towards the earth, but you don't feel your weight. You feel your weight when you actually come in contact with the earth, when you're standing or sitting or something, and the earth is pushing back up on you. That's what you feel. You feel that normal force pushing back up on you. That's why your feet start to hurt, because the earth is pushing on your feet. If you stand for a long time, your feet start to hurt. That's your weight causing that, right? Why do astronauts in the space station not feel weight? Because they're falling towards Earth, but they're moving tangentially to Earth fast enough that they, instead of falling towards the surface of the Earth, they fall over the horizon. So every time they fall, they're actually going towards the horizon fast enough that they're just falling back to the same distance from Earth. What's up? Yeah, go ahead. What did we do wrong? Oh, nice. Yeah, you deliver.
They're stuck in the box.
Two.
Yeah. These are my good friends. This is Big Ugly. I'm Little Ugly. And this is Wheelie Ugly here. So these are our friends. These are my good friends. They're both on North Campus for the most part, but Wheelie Ugly makes his way everywhere on all campuses throughout the entire 18 county area. Because he's in charge of all our computers and making sure they work. And he brought me a new, thank you. Yeah, I can get those for you in just like 1 minute. Yeah. Okay, we're going to finish talking about mass and weight. So why do astronauts not feel their weight in the space station? Because they're falling at the same rate as the space station is. The space station is falling around the Earth and they're falling with it. So they never run into it. So they never feel it pushing against their feet. So they feel weightless. It's the same as a skydiver, except a skydiver feels some air friction as they're going down through the air. They feel some air drag, right? So, and also when you're in the space station, you don't really perceive yourself falling towards the surface of the Earth because you're not falling towards the surface. You're falling over the horizon. Every time you're moving forward, you move forward and you're moving away from the Earth, but the gravity pulls you back towards the Earth. And so you're actually staying at the same distance from the Earth as you fall around the Earth. You know, orbiting is just falling around the Earth. And so you never run into anything, you never feel your weight. And that's weightlessness. So that's what that's all about. Astronauts certainly feel their weight when they come back into the atmosphere. When they come back into the atmosphere, they're falling through the atmosphere, and the atmosphere has so much force that it pushes on the capsule with that the astronauts feel up to 10 times their weight. They don't usually feel it in their feet, because if you go feet first into the atmosphere as an astronaut, if the capsule was built so that your feet were going first, you would get shin splints to the degree that you wouldn't be able to walk for months. So what they do is they put their backs to it. So their back is actually towards the part of the spaceship that's going into space, and your body can handle a lot more stress in that direction. So that you can actually walk out of the space capsule. But if you're a 100-pound astronaut, you'll feel like 1,000 pounds when you're going through the atmosphere at the maximum acceleration that you feel going into the atmosphere. So the weight, which is the force that you feel as you run into something, that's what your weight really is. Usually we're running into the Earth as gravity pulls us into the Earth. Your weight is really just that thing pushing back on you. Yes, what's your question? Oh, no question? Okay. So that's mass and weight. And of course, mass, your weight is dependent on your mass, but it's also dependent on how much gravity you're feeling, right? And it's susceptible to Newton's second law. Force equals mass times acceleration becomes force equals mass times gravitational acceleration. So on the surface of the Earth here in North Platte, we're about 2,000 feet-ish, 2,800 feet above sea level. So we're actually further away from the center of the Earth, which means we actually feel a little bit less gravity, because gravity is dependent on distance between massive objects. We feel a little bit less gravity here, not much less, but a little bit less. If you go on the top of Mount Everest, it's a little bit less too, not much less, but a little bit less. If you go down to Death Valley, which is closer to the center of the Earth, you feel a little bit more gravity, not much more, but it's a little bit more. Right? But if you go way out to the moon only feels a fraction of what we feel of gravitational acceleration from the Earth's gravity. A small fraction, a tiny fraction, like 1/10. It feels, because it's so far away, it feels much less gravitational acceleration than we do. So anyway, that's weight and gravitational force. And here they have a new equation. This is a new Newton's law. Weight equals mass times gravity, right? Where gravity is 9.8 meters per second squared. And we've already used that before, so that's nothing new. If you go to the moon, it's about 1/6 of that. Right here, they mention that, 1.6 meters per second squared. That's because the moon is both smaller in mass and smaller in radius. You combine those two things, and you get a smaller overall weight on the surface. That's the same, and actually, if you're on the surface of Jupiter, if Jupiter was a solid planet with its current mass and diameter, the surface of Jupiter, you would have a much smaller weight, because you're so much further away from the center of the mass of Jupiter. And the density of Jupiter is actually not as great as, well, I guess the density radius ratio is not as great as Earth's. So anyway, because it's a big gaseous ball of, it's a big ball of gas floating around out there. So they do some examples with this, and we've done this in our other problems. We don't have to do it again. And that takes us all the way to section 5.5, which we will carry on with on Monday. Have a great weekend. No lab. Enjoy your freedom. We'll see you later.
Have a good weekend.
Missing some facts
I'm missing some facts.
on this little, I like this.
So this,
Yeah. So,
I made this poster.
okay, the Atlas. project. Was
The Atlas, that was actually the Saturn V.
Saturn V, yeah.
The Atlas was before. that.
Saturn
So
V.
you guys,
Saturn V was, and is, I believe, still to this day, the most complicated machine ever built.
it's probably true. I don't know if that's true because the Russians built some pretty complicated rockets, but I think the Saturn V was more complicated. I'm not sure if it was more complicated than the space shuttle, but it probably, they were definitely on par with each other. For sure, it was one of the most complicated things we've ever designed.
I believe it was. Bringing in, and he said, yeah, we're sitting on top of that during launch. It's shaking. And you're thinking, the most complicated machine ever built by the world.
Yeah. By many groups of lowest bidder.
Yes.
Yeah, it's pretty funny. Well, you see,
But that
it's possible. I don't know if he ever flew that. He flew the Atlas.
was the Atlas.
He did flew the Atlas. It might have been the other one that flew with John Glenn was Gus Grissom, and he was on Apollo 1. He's the one that died on Apollo 1. And I think he was the only astronaut from the original Mercury 7 who flew the Atlas that actually flew on the Saturn V. So it might have been Gus Grissom. But John Glenn was still in the space program at the time, so he could have said it because he did a lot of the testing of it. But yeah, but
I can't
it's
think which one. I gotta look that up.
but one of the things that was, and that was actually said many times, and it was said with Apollo 13,
Yeah.
especially because when they got to the point where they're like, we're running out of CO2 scrubbers in the capsule, and so we went over to the lunar lander to borrow some from there, and they're round, and ones on the capsule are square, and we're like, or no, it was the other way around, it was square and the other way around, and they're like, really? Well, this is what you get when you get the lowest bidder.
Right.
It was two different companies that built these two different things. They didn't even communicate with each other about things like this.
They learned some lessons on that one.
Yeah, and that's actually where this is, and it was during the moon program that duct tape became such a valuable thing, and people started to realize we should keep this in our house. This is an important thing because they used that to connect those square cartridges into the round hole. And they used like a hose from one of their suits and all this other stuff, but they used an entire roll of duct tape. So yeah, there's some great stories from them. I actually have a bunch of books of them, some great stories from them. One of my favorite ones was still my favorite scientist from America is this guy here that's
Makes you wonder why architects will not name a 13th floor in a building. It goes 12, 14, yada, yada. Still, but they named the rocket Apollo 13.
yeah. Well, and
That was too superstitious.
and all the people that were like interviewing the astronauts for Apollo 13, they kept mentioning that, and the scientists and astronauts are like, "Oh, I don't know about it." All this stuff. But they were actually really lucky to get back. It was incredible. But this guy right here is named Richard Feynman, Dick to his friends, and when he was at Princeton at a very young age, I think he was 16 during World War II, and when they started the Manhattan Project, they went around to all the universities and got all the best experts on nuclear science and brought them to New Mexico to work on the Manhattan Project. And he was one of them, and he was 17 or 18 years old. He was the youngest one on the project. And they put the laboratory, which is now called, I don't know what it's called, but it's on top of a big bluff, on top of a big mesa. So it's completely surrounded by cliffs. And the only way that you can get up there is by this back and forth scissor thin road, and they would take him from Albuquerque or Santa Fe, I can't remember which, and they would take him up in buses, essentially military buses. And then they would get off the bus at the top outside the gate, and they would have to go through the gate one by one. They'd check their IDs and everything else. Well, they were still building the place. There were construction people everywhere around this thing. And as Dick is in line there, he's walking up and he's noticing there's a big hole in the fence where all the construction workers are going in and out because they just didn't want to bother checking in, checking out because they got work to do. They got deadlines to do. Construction workers, you know, they're some of the scientists. They're just trying to make fence. We put the thing up, we'll take it down. And so he goes in and he checks in through this thing, and then he goes back into the hole, comes out. And then he goes up and he checks in and goes back through the hole. He does this like 7 times before the military police realize that they checked the same guy in 7 times, and then they put him in the bridge. And Oppenheimer himself, the head of the Manhattan Project, had to come down and get him out of prison. And then he discovered later on that all of the locking file cabinets where they kept all the top secret information had this glitch in them that if you rolled the dial on the thing, it would bump up the lock if it was open. And everybody kept it open while they were in the office. So he went around to everyone's office and talked to people. And while he talked to them, he put his arm on top of it and just twiddled this thing, and he would figure out everybody's combination. Well, what he discovered is that everybody on base had the default combination from what it was given to them. They never changed it. And so later on, when they needed some top secret paperwork from some guy that was off doing some other thing in some other part of the country, he broke into their office and took it out. He got in trouble. But the same guy, when he's older, in the 80s, in 1986, when the space shuttle exploded, they asked him to be on the committee to figure out what went wrong. It was like the dumbest mistake ever, because whenever they form a committee like this, they want people that will follow the narrative and do what they're told and come to a meeting and have a committee. They'll have this meeting and decide what they're going to do, decide what's going to be wrong, and then go find out. Yeah, they just wanted him to be compliant. They have this meeting and he's not there. And 2 weeks later, he's still not there, and they can't find him anywhere. I mean, this is not modern day. This is the 80s. Nobody had a cell phone.
Right.
And finally, he shows up to this meeting, and when he shows up, he grabs somebody's ice water and puts it in front of him. And they say, "Dick, what are you doing?" And he says, "Well, why don't you guys tell me what you've learned here, and when you're done, I'll tell you what I've read." So they talk, and they figured out what went wrong. They've got all these theories about what went wrong. You know, they've decided what went wrong. And they're going to blame it all on the engineers at Thiokol, because what went wrong was that the rocket exploded, and that killed the whole, you know, that exploded the tank, and that exploded the space shuttle. So it's Thiokol's problem. Dick said, when they were done, he said, "Well, you're all wrong. First of all, you have no idea what went wrong because you didn't ask anybody who knows. For the past 2 weeks, I've been down in Texas talking to the people that know, and then they sent me to Thiokol in Utah, where they build the damn rockets." He says, "I know exactly what went wrong." And he pulls out this rubber gasket from his pocket and drops it in the ice water. And he says, years have gone by since we know what went wrong with this rocket. He's like, the engineers at Thiokol wrote memos, and they have them still, to their leaders saying, you cannot launch this rocket when it's below this temperature. And he pulls this piece of rubber out of his glass and throws it on the table, and it shatters. And he's like, that's the rubber that's on the space shuttle. That's what went wrong.
Made a documentary about it.
Yeah, and they made a huge documentary about it. And they said, when Ronald Reagan called up and said, you must launch this rocket because we have a woman on keyboard that's a teacher, and we need to make this, you know, a political stunt. That's what went wrong. You listened to the president or the White House, whoever made that decision, probably the president, instead of listening to the engineers. You all are stupid.
A couple times.
Yeah.
Somebody gave me a quote yesterday. A lot of smart people think they're way smarter than they are, and therefore they do worse than dumb people. And it's very common to be utterly brilliant and think you're way smarter, or that you're way the hell smarter than you are. And I was like, who's that? Dr. Laura.
Yeah, it's a pretty common phenomenon, unfortunately. But the smarter you are, the more responsibility you want from you. And then if you think you're way smarter than that, then your screw-ups tend to really screw up.
Listening to my ex-wife.
Yeah, engineers make a lot of really good, one of the worst ones that ever happened was an engineer who designed a walkway in a hotel. And the walkway was supposed to be hung from single rods, these huge threaded rods. You ever heard of this Hyatt
Yeah.
hotel disaster?
Kansas City.
Right, in Kansas City. And he designed it perfect, but he never checked to see if they built it right. He was supposed to, that's his job as an engineer, his job is to inspect the property, or to give it, to tell an inspector to inspect. What they did is they did a set of rods, bolted it off to the first landing, the first platform, a new set of rods, and a new set of rods. Well, the problem with that is that the bolts were designed to hold a single platform. Those top bolts were not only holding that platform, but they were holding all the way from the bottom two platforms. So they were not spec. They used the same spec. The way that he designed it with single rods, those bolts were only holding up the platform they were holding up. The bolts were holding up all three, but the nuts were only holding up one platform each. But when you stop the rod and start the rod again, that top bolt is holding all of the weight below it. And it just, they had a party, they had hundreds of people on this. It completely collapsed. It was 40 feet up. All those people died. And everybody underneath it died. It was, you know,
I've
this
shown
huge
the
deal.
video in last period when the subject has come up about decks
Yeah.
and loads. I
Yeah.
said, that's not our job.
No, that's an engineer's job.
And
he
I
should have
said-
checked.
If you have, I said, that's why I like blueprints stamped by, with an architect, and hopefully stamped by an engineer.
And it should
It's
be
on him.
followed to the T.
And I said, our job is to build to the plan.
Yeah.
If so, and if you deviate from the plan, that's on you.
Yeah, well, and it's on the inspector as well. Like the engineer should either inspect it himself or he should hire an inspector to go in. That's also on them. They should be checking on the people building, because people building are not always, they're not always thinking of structural things. They're just trying to think, I need to get this done. They got other jobs to do. They do it all in mind. They're not getting paid $100,000 a year. They're getting paid lower wages. They have other things on their mind.
And
So
we
it's,
have bosses that tell us, shut up and do it.
yeah, it's their fault for not following the plans, and that has different consequences than not inspecting the work. They both are at fault for different reasons at different levels, but yeah, I show that one all the time to my students because it's both bad engineering and bad building. But let me get you some iPads.
Well, I was gonna ask also, like, perimeter.
Yeah,
I haven't seen that.
sure.
Wasn't the other one that like the size of a farm?
Yeah, it was much bigger, but it also had a much bigger thinking space, and it was also full cover. So it was different from this one. But this is it. Yeah, it's very cheap. But my next purchase for this one is gonna be, I'm gonna put a HEPA filter on the top here so that it doesn't put any fumes in. But this is the building platform here. This is material fencing. It's kind of a composite plastic, interesting material. And the clear material is actually water soluble, so that you can actually remove that, so that you can build places with voids.
Yeah.
And then you can, this out. But this stuff is super strong. This composite is super strong. It's infused with something, I don't know what, but it's a very strong material.
What's this?
Oh, it's a tank, a water tank that I did for an experiment a few years ago. And I just put it together with some acetone. and-
No, this thing.
Oh, can't you tell what that is?
It looks like it's for cutting. Oh,
That's my homemade, what do you call that saw that's like, built like that? They call it that you can tighten.
A cheese slicer?
No, like you have one in your room. that
A
has-
pit saw.
Is it a pit saw? Because you can tie it.
My pit saw the blade from the middle.
Well, no, what is the saw called that has the?
Oh, a bow saw.
A bow saw. So this is it's a bow saw, it's an electric bow saw.
Looks like a frickin'
I
saw.
was trying to see if I could bend this quarter inch acetone and heating it up using this wire, but I can't, it's not hot. If I turn it up to where it's hot enough, it starts, it's like melt, you can see here it melted
the rubber off the wire. But this is when I built my solar system, I built a scale model of the solar system a few years back when I did this. And the sun was 2 meters in diameter, and it was over here by the university farm. And Pluto was the size of the head of a pencil, and it was by the river. And all the planets were like Jupiter was a basketball, the Earth was like the size of a pencil. They were all scaled, they were all painted, and we set them all up with signs and information on all of them. Let people take a tour. Most of it was along this walking path. There are a couple of things that have been there's some. I really wanted to do a radio, so we noticed was do something in downtown. But that should.
No, the men from Mars, and the men from Venus. And it's all the rest of the genders. Why don't you camera the recent?
Eyeball, that'd be awesome.
Well, actually, we're going out Wednesday. Sorry, look better like this does, but we're gonna have another one. The biggest one is that.
I went in for ad and it started back.
Yeah, so these ones will track, you can set them up so that they'll. These ones back here, the smaller one my dad gave to me, and I've actually been shipped that one back to my brother. Because he wants that. So the big one, that's its image. That one was actually given to me by the Girl Scouts, we started with something. But I think we got this from something you want. It needs to be cleaned, it needs to be fixed.
Outside of that water.
Yeah.
Infrared.
The infrared ones that are good, they have to be cooled, so that's what it's the whole back end of it, it's just a cooling.
Yeah,
So what's
see.
essentially the same thing as like CPU, it's just good.
I'm showing Mary.
Yeah. No, I think it'd be cool is to get one of those home astronomy rooms so that you can set up your telescope and you can set up all the time.
Yeah.
Then you can just open it, you can rotate. It's so cool. Because they're coming down to about $5,000. It's super cool.
Oh, After backyard.
Oh, I've seen him on YouTube.
Yeah, he got one set up in his
Yeah.
backyard. He's in New York. And the filters, he can. That's really cool.
Yeah, that would be fun. It was like when I was at BYU as a student, that was just so much fun because they have, I don't know how big that was, but they were 24 inch telescope on in the observatory. And that one was connected directly to high resolution screens. So they would get up there and point it to Mars and focus it really well. You could actually see the polar ice cap in Mars. You know, that's just so cool.
And your road is right at the wall.
Well, yeah.
It's taken over 2 times.
Yeah.
Wow. So,
I grew up in Cleveland. One of the little girls that I went to kindergarten with. And her father was the scientist running the observatory there. All kinds of things. And they big, so
Super cool. I'd like to go see one of the big, so telescopes nowadays, instead of having one big tube with one big mirror, now they have multiple mirrors. And the mirrors can adjust, they can adjust the mirrors to focus. And it's just amazing. It's just so cool.
and I asked him about the sun, and he did something, I don't think it was the sun, but then he stuck it up there and said, now, piece of paper. And you were like, he said, it goes right to the back of the head.
You can do that, you can burn holes in paper with that. Not through the back of the head, but you can easily
Go
burn.
blind?
Well, you can easily burn holes in the eye. You can do that. You can do that. It doesn't take much to look at the sun.
No, I've sunburned my eyes skiing.
Oh, yeah, that's a good.
No. That was not pleasant.
I've been
And that was with sunglasses
Just in the side.
that didn't have sights. Because I bought those REI sunglasses, other size, but I can never get glasses with the temples that far. They all sit on the top of my ears.
So,
And it's really uncomfortable.
you know, the best.
Oh,
No, I got $3 safety glasses
Oh, yeah, you're good.
because the temples are barely curved
Yeah.
and they go,
Right.
they fit.
Yeah.
$3.
Like mountain climbers that spend a lot of time in the snow, they started this company called Juno. They're pretty famous. Hiring, high class company, they make like fashion ones. But they used to just be 2 round discs with leather everywhere. And then the temples were such extreme wear, so you could just roll them out and they roll around your ears.
That's what I had from REI.
Yeah.
I think REI was because the REI were the cheaper ones.
Yeah.
But that it was like, okay, these things are gonna pull my ears off the side of my head.
Yeah, they can sometimes be able to.
that's a theory.
Yeah, those are nice. But I've been thinking about buying a couple of astronomy cameras, I just haven't done it yet. But, I also want to buy a couple of telescopes, I want to get I want to get another.
Astro camera. You can also.
Essentially just takes the place of the eye piece, and people still really like. I actually have a cheap one. I've never used it.
The camera I have, you can get sent off and get converted to infrared.
Yeah,
You can just use it.
I can do that.
Yeah.
What you do is you take the camera apart and on top of the CCD chip, there's actually a filter that filters out all light except visible. So that you can, because if you use a CCD without a filter on it, it will detect infrared, ultraviolet, it detects all kinds of light. It'll detect X-rays. And so I went in
That's
and
the camera with the telescope.
On a server.
so what I did is I went in there, I
Which
took
is
an old
67 Ford telescope.
That's a cheaper.
But anyway, what you do is you take an old digital camera and you get in there and take it apart and take that filter off and you replace it. And it's kind of tricky sometimes depending on the camera. But you replace that filter with a couple of sheets of blackened out film that's been exposed. So you know, at the end of a roll of film, you have that black part. That was from when you pulled the film out to begin with and all got exposed to completely
I
black.
still have 35
Yeah, so do I had 2 of them, maybe 3 actually.
I have the full dark to develop there.
I actually built a dark room for my grandpa. We're like old people. Come on.
And my dad had dark.
Yeah.
So I
I
think
think we still have all of the dark room stuff there. Parents' place down in the basement. Back away.
Good old days. But anyway,
Well,
you
that's
still
what they
use
taught
that.
us in high school.
Yep.
We had graphic arts and we did photography and
I don't know, man.
Like, so my grandfather was actually a professional photographer. And he did mostly like postcards because when he traveled as in the military, he went to all kinds of exotic places. So he'd take those pictures and sell them as postcards. And when he when he got really good at it, he started doing stop time photography, where you link a flash to a microphone. So the microphone causes the flash to flash. It's the switch for the flash. And then you go into a room and you take a glass bottle or something, and you hit it with a hammer. And as soon as you hit it with a hammer, the flash goes off, and you get this incredibly high speed image of glass breaking. Like it's just the whole bottle is shattered, but it still looks exactly like a bottle. You know? Or he would do multiple flashes and take a picture, and then you would see, and you would have rolling film instead of just still film. And you'd see it shatter, still the same shape of a bottle, and then you'd see it, you know, in different shapes, or like the bullet through the apple kind of he did back and stuff, milk dropping on the table. He did all those fun pictures, they're super cool. It's super fun to look at these different things that he would do. He was a good photographer, but I think I told you this, I actually found his pictures from Hiroshima, because he was the first, did I ever tell you that? So he was an Army Corps of Engineers, and his specialty was infrastructure. So when a city was bombed, it was usually his job to go back in and get the power up running and everything else. And he was in the Philippines when they dropped the bomb on Hiroshima, and he got a call saying, we're sending you in to redo the infrastructure of the city. They never told him it was bombed. They just put him on a plane and sent him. So he took 5 of his officers, a couple of jeeps, and got on this plane, and they flew him in, and he landed in Hiroshima the day after they dropped the bomb, literally the day after. Less than 24 hours.
His grandfather died of cancer.
Every one of them died of cancer, and my grandfather included. My grandfather lasted the longest. He died when he was 82, I think. But he had, for his entire life, a tumor in his brain that was just growing and growing and growing. Eventually, it just cut his brain off, and that's what he died from. But it was the size of a softball. He had major vision problems from it. The rest of them died from other types of cancer before.
And nobody got a, oops, I'm sorry,
Oh yeah, they all got paid a lot.
really?
Oh yeah, they were all millionaires when they died. So yeah, so they got huge payments from the military.
They got good life there.
Yeah, that's what it was. It really was. So my grandfather wore weird glasses because they had like, instead of like 1 or 2 lines in them, they had like 50. Because one of his eyes was being affected by the pituitary gland so bad that it was causing his eye to look down all the time or something. And so in order to make it look up, they put a Fresnel lens. You could see forward. All kinds of weird things. They had all kinds of mental issues. But he brought with him his Graflex 5x5. So Graflex is the camera that you see in the old like Spider-Man films with the handle and the big bulb, and it has the bellows. That's the Graflex. The negative of the Graflex was 5 centimeters by 5 centimeters, so it's a huge amount of resolution. You take like Ansel Adams used Graflex because it gave you so much more resolution than like a Rolleiflex or one of those view cameras where you view from the top. Those were all 3x. So it had a smaller frames, lower resolution. The Graflex also had a longer focal length, so you can get better resolution at distance.
I think you can get like 7
Oh yeah, you definitely could. In fact, Ansel Adams used it.
Yeah.
Many of
And
them.
I thought they were fun.
Yeah, so he had his Graflex 5x5 and took tons of pictures of Hiroshima. And he mostly stayed away from the gruesome stuff because he was an engineer. He was more interested in the damage to buildings and everything.
Right.
Like this, but we have tons of pictures. We actually found them all. And we brought a bunch of them back here to Nebraska, and we hopefully put a thing in the museum. So, but it's really kind of one of the things they took a picture of was mini kamikaze submarines that they had, because he was also in charge of disarming them. So we found this factory where they made a bunch of these mini kamikaze submarines that like torpedoes hit one person. A lot of explosives. But he had a really funny story too when he was up there disarming. The day after the war ended, it was towards the end of he was there for like a month or something. So towards the end of his time there, he was going around to different installations and telling them the war was over, stand down, turn the weapons, go. Because the government wasn't. And he went up to, there was an arms depot up in the mountains. And he was tasked to go up there, so he loaded up his Jeep and a couple of his guys, 50 caliber machine gun. The only guard was this 12-year-old kid with this old action rifle, shaking and shooting. And he's like, his job was, if he was threatened to kill him, to mow him down. My grandfather was to kill a 12-year-old. So he's just sitting there thinking, he's like, so he gets out of the Jeep and he walks up with his hands out in his wallet, just like this, and says, they don't speak English now, and says, opens this up and he does this. Does this. With his Montana some city in Montana library card. It just holds it up to him, doesn't say anything. He just points at it, says this. The kid looks at it. Puts his gun on and watches. Like, I think it was Mizzou.
They were still flying island. 70s for Japanese soldiers, but I had no idea what war was.
Yeah, there's so many remote islands. It's crazy. And I would have hated to be out there because, like, I met somebody here when we moved here. We met a guy that actually fought on Iwo Jima. He was actually, so you know that famous photograph of Iwo Jima where they're holding the flag up? That was staged. Okay, most people know that now. But he was one of the people that was staging it. So he was actually just outside the photograph, holding up the guy that's on the very, very edge of it because he couldn't keep his balance on this perched on this rock on the side of this little hill thing. So he was just holding him up, and his hands are in the picture, but he's not in the picture. But he is actually from Montana. And he died a few years ago, but still has plenty of people there that understand. But he was actually shot on the things that he saw were just terrible because the people were told by the Japanese government that the Americans are all these terrible things. And so they literally ran off cliffs to get away from the Americans. Like 2,000 people died in one afternoon, where the entire village just ran off a 2,000-foot cliff and fell to the rocks. And the Americans were just standing there. They're like, we weren't going to hurt anybody. As long as nobody fought us back, we were fine. And we just had to watch that. And it just happened over and over again.
Well, it was the same in the tunnels. They didn't want to come out of the tunnel. The soldiers.
Yeah.
They'd rather die.
They were so propaganda.
I had a horseback riding instructor in high school, Poland, who he was in Bucharest. And one summer he went around in the crutches to climb on your arm, and I always saw the number on his forearm. There was one summer, he just his white shirt soaked with sweat, he had it unbuttoned. I'm like looking at it as I go by my horse. He's got fucking bullet holes. He'd been executed, thrown in the pit,
Waited till night and crawled out.
because they didn't bury him. And
Because they had more work to do.
his wife thought he was executed. He thought she died as a camp, and they found each other in New York City after the war. And they started this stable up there in Connecticut, Ridgefield, Connecticut, just up the hill from high school. I was just like, to meet these people, this is history. And then I worked across town and on an estate, and our housekeeper and cook on the estate was a great grandmother. She took care of her grandmother. And when I met, in 1974, when I started working on that estate, the woman was over 100. She was born, 74, because she was born in 1868. She was over 100, and when I graduated high school, the woman was still alive, sharp as a tack, and would sit out there in a rocking chair with a little dulcimer and sing her gospel songs. And you could hear her anywhere, and you were just like, I am talking, this woman's parents were slaves. And you're just like, this is living history.
So here's one for you. You remember Sarah, who used to be a biology teacher. Sarah, so when I first came here, she was redheaded and all this, and she died 2 years ago. I can't remember that. You remember her?
Yes. Well,
Yeah, anyways, she was here when I first got here, she probably retired 5 years ago. Her dad was born in covered wagon crossing the plains. I'm like, no, you gotta be kidding me. She was almost 70 when she retired. Her dad was 70 when she was born. He was, shall we say, hero.
Wow.
He'd been married to 2 or 3 other women who had died and had children by all. But he got married late in life to another woman that was young, actually, you know. How do you got to marry a woman who can still have children when they're 70? My goodness.
A friend of mine in college, Darius Carrera, his father, not father, his grandfather was the king of the tribe back there in Kenya. And I made some joke with him on his dad. I said, "That's the tribe." He says, "No, man." So, and just as a smart ass, I'm like, "Yeah, how many wives does he have?" He said, 7. And I'm like, "What's wrong with him?" It's like, what do you mean? You know, I'm like, "I got 1 girlfriend. That's enough."
Let me get you some iPhone.
Yeah.
You care which one's
Where? No. Where you guys go started?
I actually really want to get a couple of cold pieces. Really, yeah. But if I could even get a rich position on. But they do a really cool, Western reenactment. Well, just, I think it would be- Well, go to Texas. I still remember being in New Mexico, Texas for God assets. But in New Mexico, they're always used to people back. Always. Let's see, Arizona. Always. You can hear them. I see you gotta do with. That's all I got. Just get a bunch of really great customers. They shoot full on ones. Okay, that's something. Such a classic, I mean, it is the gun. It is the gun. That is.
After years. I ended up buying my first 3 boxes.
Buy ammo online. Just the brand. Yeah, the only gun that I know for a bomb. I thought about building. nobody wants to sell them. And for us, we build, we have a product or product, you know. We can actually. So, yeah, so when I bought these, I needed to have all of the, visual access. So, but I didn't have time to do it. The friend was very. Down behind me as a contractor. Essentially just, we shoot to his house and something about calibrating machines. It was actually. It's like, we have to build something to calibrate it. So he was saying, he gave him serial, the first one, the second one, 2. Oh, man. All right, we'll see you guys later. Thanks again.